All right, guys. So this is called the polygon angle sum theorem. There's two theorems. They're pretty simple formulas. But before we get into talking about them, we need to discuss some vocabulary. We need to know what polygon is. Okay. This is the definition that you see most of the time in regards to a textbook. Just Google polygon, something like that. It's probably going to come back with the phrase many angles or many sides. Okay. Poly means many, right? If you guys are in, maybe world history, start talking about polytheistic people, right? Okay, like the Romans and the Greeks and all those types of people. They believed in many gods. Okay, so many was the word poly. Okay, gon referring to angles then. Okay, so this is a Greek origin. However, to be a polygon, what we're thinking about is a polygon is a two-dimensional shape. Okay, meaning that it lays flat in the XY plane. Okay, and it has all of these following requirements. Okay, so each segment intersects exactly two other segments. Each segment intersects exactly two other segments. Okay, and generally speaking, we do that at endpoints. So each segment is going to have two endpoints, and it needs to intersect two other segments at their endpoints. All right, I'll draw you pictures here in a little bit of what polygons look like. There are no curves through them. Okay, no curves. No circular portions. Like I said, all segments are coplanar. That basically means they're all two-dimensional, meaning nothing is coming at you or going away from you. Okay? And then the last one, it says the figure must be closed, meaning that it basically kind of ties into that first statement. To be closed, every single segment needs to intersect two other segments. Okay? Otherwise, you have a gap, an opening, which would not meet the requirements of being a polygon. Okay? So I'll give you a couple examples here of things that are polygons and things that are not. If I look at those shapes on the left, those are all polygons. Okay? They're all comprised of simply just segments, and choose any one segment, and it's going to intersect exactly two others. Okay, so if I take, let's just look at this first one here on the left. If I were to take that segment right there, does it intersect exactly two other segments right there and right there? Right? So that's the one segment, and that would be the second one that this one intersects. Then if I take this one, okay, does it intersect exactly two other segments? Does it intersect that one and that one? Does that make sense? Okay. Does this segment intersect exactly two others? That one and that one, right? Every single segment up there that comprises that polygon on the left intersects exactly two others, and it does so at those other segments' endpoints. Okay. There are no curves there. Okay. It is coplanar. Okay. So I'll give you an image of something that maybe has all these characteristics, but is not coplanar. So if I were to give you I think in understanding what polygons are, and a lot of these shapes that we talk about throughout the rest of the year, it's important to also talk about examples that are not polygons. If I look at, let's see here, let's just do, all right, would everybody agree that that is a polygon? That's no curves. Each segment intersects two other segments. It's all coplanar, right? No longer a polygon. Okay? Still two segments intersect every other, or each segment intersects exactly two other segments. No curves. Okay? But what happens is now we have segments that are not coplanar, right? Okay? And essentially what it does, eventually we're going to learn some rules and properties about the angles here, and this just generates a lot more angles that are a little bit kind of weirder to deal with than if all of these points were coplanar. Okay? Now eventually, maybe in higher levels of geometry and other areas of math, maybe you start talking about that as being kind of a polygonal type shape, okay? But it's not a polygon. Is that right? Okay. You know, maybe eventually we do something like this. Oh. So maybe we end up with like a three-dimensional shape here. Maybe even close these off. Now that's a pyramid, right? Does that make sense? Okay. And the sides of that pyramid are all polygons. Okay. So we say the pyramid is polygonal because of how its sides are made up, but that shape itself right there is not a polygon because not all the segments are coplanar. Is that all right, everybody? Okay, so this one would be non-polygonal. Yep, that is one that's non-polygonal because we violate this statement here. So essentially, anything that violates these four ideas here, Colin, would generate something that's non-polygonal. So looking at this one here, this Pac-Man looking shape, okay? Non-polygonal because it has a curve in it, right? Okay. Look at this one down here. It looks very much like some of these on the left that are yellow, okay? This one right here, okay? But if I look at that segment right there, how many other segments does it intersect? Yeah, three. It intersects that one right there. It intersects that one right there. And it also intersects that one down there, right? Okay. So you see how if that thing was like made out of wire, like a polygon was made out of wire, it kind of folds over on itself there? Does that make sense? Okay. So if you ever see in a shape where it's folding over on itself, you've got that idea that you're violating the idea that you need every segment to intersect exactly two other segments. So that's not a polygon. This one here, okay, because that is not a defined segment there, and it's open, we violate the fact that that's a polygon. Polygons have to be closed, right? Okay, so that's not closed. That one up top right, okay, again, that one up top right is not a closed polygon, even though each segment intersects exactly two other segments, doesn't it? Okay, it's still not a polygon. Okay, it's not closed. There's not an interior. Does that make sense? You need an interior for a polygon. So, all right. Now that we have an understanding of what polygons are, we're going to now look at the polygon section. We're going to look at those shapes on the left and start talking about how can we classify those. Okay, so we start breaking those down even further. And there's two types of polygons that we're going to deal with. One of them is called a convex polygon. Convex polygon. These are the ones that we prefer. Okay, we like to work with convex polygons. Okay. The definition is weird. Okay, but the definition, and this is the way we set definitions up at the beginning of the year, they have to be written so that absolutely no counterexample exists in or nothing accidentally gets classified as convex that really isn't convex. Does that make sense? Okay. So I don't want to write a definition that maybe misclassify something. So a convex polygon is a polygon such that no line containing a side of the polygon contains a point in the interior of the polygon. Okay? That's the mathematical definition. I will explain to you a way for you to recognize that a little bit easier than using that definition. Okay? But that is the definition you'll see on your tests and quizzes. A polygon such that no line containing a side of the polygon contains a point in the interior of the polygon. It's basically a test. Okay? That definition, you run through a test of highlighting a line that contains a side, and just test, does it go through the inside of my polygon? Does it go through the interior? All right, and you have to do that because it says no line containing a side. You have to do that for every single side of your polygon. So, I'm just going to jump to Desmos real quick. Not Desmos, GeoGebra. And show you a couple examples of things that are convex. All right, so what you end up doing is you take just any line. Okay, I choose a segment of my polygon. I'm going to say A to B. And I'm going to look at that line that contains segment AB. Does that make sense? Okay, so that's the phrase that no line containing a side of the polygon. So that's a line that contains a side of my polygon. Does that red line pass through the interior of the polygon? No, it does not. Okay? So far, we currently have a polygon based off of that test. But how many sides does that polygon have? 5 sides, right? Okay? So we have to do that test 4 more times. Okay? So I'm going to take B to C, and I'll make sure that that blue line does not pass through the inside of my polygon. Does that make sense? And I'll go C to D, and make sure that that green line, that's a terrible color, that green line does not pass through the interior. Then we go F to D, and make sure that that purple line does not pass through the interior. And then the last one would be A to F, and make sure that that orange one does not pass through the interior. Does that make sense to everybody? Okay. So, this was the original polygon, right? Okay. None of the lines that contain the sides of that polygon pass through the interior, so that thing then is identified as being convex. Okay? Every polygon like that, okay, no matter where I move A, B, and F, as I move them kind of further out, I'm still having convex polygon, right? Okay? The issue becomes kind of like that. Okay? Does that, we'll just kind of look at one of these. Let me get rid of, okay? So is BC a side of my polygon? Is this blue line the line that contains the side of that polygon? Does that blue line right here pass through the inside? Yes. So that polygon right there is not convex. Does that make sense? Okay. Now, as you're testing that, you might have initially said, when I look at that there, right now, so far, just because that's the only segment I've looked at, that is, right now, it's classified as convex. Or, sorry, convex. Look at that one. That's still convex. Looking at that one, still convex. I have not violated that definition yet, right? It's not until I look at BC, the line containing BC, or the line containing CD, that I violate that definition, and now it becomes non-convex. Okay? Now, when it's not convex, it is said to be concave. Okay? So a lot of times the definition for concave is a polygon that is not convex. Okay? So how do I know what concave is? I got to know what convex means, right? Okay. So a concave polygon is a polygon that is not convex. You guys have talked about concavity before. Okay? Because we were talking about parabolas last year. And parabola opens up or it opens down. You talk about concave up, concave down, right? Okay? If you've ever looked at it like a spoon, obviously you've all looked at spoons, but a spoon is a concave shape, right? Okay? And the way light interacts with concave shapes. You ever look at a spoon, like the different sizes of spoon? Sometimes your image, or if it's reflective, sometimes your image is upside down. Sometimes it's not. Okay? It's how concavity kind of forces light to reflect. But concavity, okay, in all those situations, across all of mathematics, concavity is the idea that there's kind of a depression on the figure. Okay? You see how that's kind of caved in right there? Does that make sense? Okay? You see how this side here is kind of caved in? All right? On this one here, are there any caved in sides? No. Okay? So the way I look at it and remind myself, instead of remembering that long definition for convex, I look at my picture and say, are there any sides that are kind of pushed in? Okay? Anything that looks like maybe, after Cora starts driving for a while, like her bumpers. Okay? Caved in, right? Okay? So anything like that is considered a concave image. Okay? Concave polygon. Is that all right with everybody? Okay. The reason we need to know that is because, and the difference between these things is because some of our theorems and definitions are going to say this is only true, this only works for convex polygons. Okay. Polygons are named based on the number of sides. The number of sides that they have is identical to the number of angles that they have. So some textbooks will say polygons are named off of angles. It doesn't matter. Okay. You guys have all heard, obviously, we talked about triangles, right? Okay, that's our smallest polygon that we can create is a triangle. We didn't talk about quadrilaterals. That's with 4 sides. And then after quadrilaterals, it's what? P?
Pyramid.
No. What means 5? What's the word for 5? Pentagon, right? Okay. So you have pentagon. Then 6 is hexagon. 7 is, okay, you got 2, it's either heptagon or septagon. Okay, either one of those. 8 is octa. Okay. 9, nonagon. Okay. 10 is a decagon, right? 11, no. I believe 11, a lot of times 11 is just like 11 and then a hyphen and G-O-N. But I believe it's real word is a neagon. E-N-N-E-A-G-O-N. 12 is a dodecagon. I think the 13 is like a tridecagon or something like that. Or something like that. All of our shapes, 13, 14, 15, even like 25, 27, 28 sides will have like these Greek names. If you just Googled like a list of polygon names, you'll see those, and they're really weird and really hard to remember because a lot of them are very similar. Usually after 10, they just start saying 11-G-O-N, 12-G-O-N, 13-G-O-N. Does that make sense? But I think it is important because in Math Excel you might see dodecagon and have to know that that's 12. But just give you, but there's patterns based to their names. Just give you a real quick polygon name list. All right, so Wikipedia gives you a way of kind of how the shapes are identified through the Greek numbers. Okay, so R5 is penta, right? R6 in Greek is hex. 7 is hepta. 8 is octa. Okay, now we use a C, right? But then you start to see So there's 13. Tri-sky deca. I can't even say half these. Tri-sky deca. 14 is kind of ridiculous. Okay, but you would just put gon on the end of these, right? Does that make sense? And that would give you those names for those things. Obviously, I'm not going to require you to be able to count in Greek. So once we get to 10, we can start saying 11 gon, 12 gon, 13 gon, that kind of thing. Equilateral polygons. What's equilateral mean? Equal side. Lateral means sides, right? Okay. So equal sides. Okay. So it's a polygon. Now it doesn't matter whether it's convex or concave. Okay. It's just any polygon where all the sides are congruent. Is that all right? Okay. Is that thing right there? We've seen this before. When something was equilateral before, it was automatically equiangular. Look at that picture up there. Are all 6 angles up there equal? No. Okay? So in general, when talking about polygons, equilateral polygons do not mean or do not imply equiangular polygons. That was only true for triangles. Does that make sense? It's only true for a select set of polygons. One of them being triangles. Okay? An equiangular polygon. Polygon with all angles congruent. Looking at that one, hopefully with that picture drawn the way it is, you can argue all those angles are the same, but the top and bottom sides, okay, those do not appear to be the same length as the ones on the left and right, correct? So it is important for you to know. Let me write something here. Okay, with polygons in general, and when I say in general, I'm meaning all polygons. Okay, equilateral does not imply equiangular, and vice versa. Okay, equiangular does not imply equilateral. Okay, it does mean that in triangles. That's the one set of figures or set of polygons that is true for. But with quadrilaterals, it's not necessary. Okay, it's not necessarily true with pentagons, hexagons, octagons, septagons. That is not a true statement. Does that make sense? Okay. Equilateral does not imply equiangular. All right. However, that does occur sometimes. Okay, so a hexagon is not always equilateral when it is equiangular. It's not always equiangular when it's equilateral. But when that relationship does exist within a hexagon, we say that hexagon is regular. Okay? When it happens with an octagon, we say that octagon is regular. When it happens with a pentagon, we say that pentagon is regular. Yes?
Why is it considered regular if it's only one of its kind?
Just the word we use. I don't know. Regular is the word that we use to elicit the idea that equiangular and equilateral is present for that shape. Okay? So a regular, and that happens throughout all mathematics. The word regular means equilateral and equiangular to it. Okay? Occurring at the same time within a shape. Okay? So when I just give you think of a hexagon, you don't have to think about that shape. Okay? Because, let's see here. One, two, three, four, five, 6 sides, right? That's a hexagon. Is that the hexagon most people think about when I say hexagon? No. But it's got 6 sides, right? It's a polygon, right? Okay. Is it regular? No. Okay. Is it convex? No. The only way that a polygon can be regular is if it's convex. Concave polygon cannot be regular because they cannot have all angle measurements being the same. One of your angle measurements is actually going to be bigger than 180 degrees. Okay, this angle. See here. See how angle E here on the inside of my polygon is going to be bigger than 180 degrees. That makes sense, everybody? So there's no way that it can be equated to A, F, B, C, or D because they're all less than 180 degrees. So that might be something you want to write down. A regular polygon is always convex. All right, again, so this is vocabulary we're going to use throughout the entire chapter, guys. So my hopes are that because I don't think we did this very well last chapter, okay? When we start learning vocabulary that might be new to us, spend some time on it initially in the chapter. Go home, rewrite these vocabulary words, read them to yourself over and over and over again. Convince yourself of what they are. Okay? Look at pictures that are regular. Look at pictures that are not regular so you can identify these things. So that later in the chapter, when we're seeing theorems that address these and we're using these words again, we can really use those theorems and understand what they're saying. Okay? If we don't know vocabulary, we really don't know anything from the theorems there. Okay? To get to our theorems, we need this vocabulary word. Okay? It's called a diagonal. Okay? You guys know like what diagonals are. Okay? If I were to move diagonally from the classroom, okay, I would move like from corner to corner, right? Okay, or from where if I'm standing back here by the door, okay, I'm gonna walk across the diagonal of this classroom. Where would I be walking to? Give me something in the room, a location in the room that I'm gonna walk to. I'm gonna walk to my filing cabinets, right? Okay. So walking across the interior is an idea or a concept that's necessary for a diagonal. Now, writing my definition that way is not a really good math way of doing it. Okay, so we write it this way: a diagonal is a segment joining two non-consecutive vertices of a polygon. Okay, what does consecutive mean? In a row. Okay, so Monday, Tuesday, Wednesday, Thursday, those are consecutive days because they're in a row, right? If I go Monday, Wednesday, were they consecutive? No, I missed a day, right? I skipped over something. Okay, so skipping over something eliminates consecutiveness. Okay, so if I look at this hexagon here, let's just look at that one there. Okay, and I look at point A. Give me a point that is consecutive to A. B, give me the other one. F. B and F are consecutive, right? So I cannot draw a diagonal to them. Okay? So I go from A to B. The only way I can do that is to draw a segment of that figure, right? So it's already a defined segment for my shape. The diagonal would be A to C. Does that make sense? Yeah. A segment that joins two non-consecutive vertices. That's a diagonal. Okay. What about A to D? That's another diagonal. A to E, another diagonal. Does that make sense? There from A, you have three diagonals in that shape, right? But what if I wanted to go from F? Is that a diagonal? Is that a diagonal? Yeah. Is that a diagonal? Okay. So there's three diagonals that can be created from every single one of those vertices. Does that make sense? So I have 1, 2, 3, 4, 5, 6 vertices, right? I could conceivably draw 18 diagonals in that shape, right? Now some of them, like F to C, that might be when I go from C to A, C to F, and C to E, that distance CF is repeated. So it might not be 18 distinct different diagonals. It might be more like 12 or something like that. There's a lot of diagonals there. Does that make sense? A lot of times when we talk about the diagonals of a figure, a polygon, we usually just talk about them from one vertex. So maybe I just say I'm going to look at the diagonals from A. Okay? Because what we are interested in with diagonals right now is what that does to that polygon. What does that segment that polygon up into? What other shapes are created there? Triangles. And what do we know a lot about? Or what should we know a lot about? What shape have we spent a majority of our time talking about this year?
Triangle.
Triangles. Okay? So if I want to learn something about that polygon, that hexagon, I can learn that information through the knowledge of what I have already developed and already learned about triangles. Okay? So when we look at this question, or this theorem here, it says the sum of the measure of the interior angles of a convex polygon. E here has to be convex. It does not work for concave. It has to be convex. Okay? With n sides or n angles is n minus 2 times 180. N minus 2 times 180. Let's write that down. While I'm writing that down, I'm going to find an applet I've got. We know how many degrees are in a triangle, right? 180 degrees, correct? We add up all three angles, okay? When I go to a quadrilateral, I want to add up all four angles. When I go to a pentagon, I want to add up all 5. The hexagon, I want to add up all 6, okay? When I get to a dodecagon, I want to add up all 12. Well, they're not all going to add up to 180. They're different shapes. They're not triangles anymore. Does that make sense? Okay? So, and this image here is on my website if you want to open up. Nope. It's my brother. He's kind of a baby.
No, 10 minus 8. Wait, what's the formula?
Oh, sorry. N minus 2 times 180. N minus 2 times 180.
Divide by n.
Nope. Just right now, don't write that bottom one yet. Don't write that bottom one yet. Okay. N minus 2 times 180. So where that formula there is coming from? N minus 2 times 180. Every time that I take a polygon. Man, this thing's slow to load. Well, maybe I'll show that tomorrow once it's loaded. How many sides does this thing have right here?
1, 2, 3, 4, 5, 6.
Has 6 sides, right? If I draw all the diagonals, how many different triangles are created?
12.
That triangle? That triangle? That triangle? And then this last one, right? There are 4 triangles created from drawing those diagonals, right?
Yeah.
So how many multiples of 180 are there? There's 4. Okay? So n was 6. If I subtract 2 from it, do I get the 4 triangles?
Yeah.
Multiply those 4 triangles by 180, right? Okay. What if I take, I'll just do a regular polygon because it's a little bit easier here. Let's take 9. Okay, so if I take 9, how many triangles am I going to be able to create here? There's 1, right? There's 2. There's 3. There's 4. 5. There's 6, and this one becomes 7. So how many triangles can I create when I have n being 9? 7, which is n minus 2, right? So 9 minus 2 gives me 7. So the n minus 2 tells me how many triangles would be able to be created inside that convex polygon. And if each one of those triangles has 180 degrees in it, can't I just take 7 times 180? So I take 7 times 180, that's how many degrees are going to be in that blue shape when I add up those angles at A, B, C, D, E, F, G, H, and I. Add all those up. It's 7 times 180. Does that make sense, everyone? Okay. We'll finish this up tomorrow. No homework tonight. We should be able to wrap that up pretty quickly tomorrow. Do some examples, and then I'll open that time up for you tomorrow. Yeah, I can do that.